Welcome to The Explainer. Today, we are diving into a really fascinating mystery at the very heart of how AI actually works. It's a contradiction that pits our best theories against some cold, hard evidence.
Okay, so let's jump right in. We have these powerful, really elegant theories about how models like GPT-4 learn when we give them examples. But what happens when new research comes along and shows that those beautiful theories are actually broken?
This right here is the paradox we're tackling today. You see, our best theory says an AI learns like a perfect statistician, logically updating its beliefs with every single new piece of data. But the evidence, when we actually test it, shows it consistently breaks a fundamental rule of that very process. So what on earth is really going on under the hood?
To solve this, first we really have to understand the conflict itself. Think of it as a classic battle, a beautiful, perfect theory running up against some very, very inconvenient facts.
So for years, the leading explanation for how AIs learn from examples in a prompt, what we call in-context learning, has been this idea that they're implicitly performing something called Bayesian inference. The easiest way to think about it is like an ideal detective who perfectly updates their theory of a crime with every new clue they find.
Now, a core rule of being a perfect Bayesian detective is something called the martingale property. And this isn't some minor detail, it's a mathematical law. All it says is that for a true Bayesian reasoner, the order you see the clues in shouldn't matter at all. The final conclusion should always be the same. But here's the bombshell. Recent studies put the top models, we're talking GPT-3, GPT-4, Llama 2, to the test, and they all failed. They consistently violate this martingale property. And that discovery, well, it challenges our entire understanding of how these incredibly powerful systems actually learn. So, if the perfect theory is wrong, what's the alternative? Well, the answer, it turns out, was hidden in a clue that pretty much everyone took for granted. A clue found deep inside the AI's fundamental architecture. And here's the core issue in a nutshell. A true Bayesian detective sees all the evidence as just a bag of words. The order is totally irrelevant. But a transformer, which is the architecture behind models like GPT-4, is built from the ground up to care deeply about sequence and order. For a transformer, order is everything.
The way it does this is through a feature called positional encodings. You can kind of think of it like a GPS for words. It literally stamps every single token with its exact position in the sequence, which explicitly breaks that order doesn't matter rule that's so critical for pure Bayesian learning.
Which brings us to the crucial question, right? If the model's very architecture is designed to violate a core Bayesian principle, how on earth does it still achieve such incredible, near-perfect performance? I mean, is the entire theory just wrong?
Well, the resolution to this whole paradox is both subtle and frankly brilliant. It doesn't just throw the old theory out the window. Instead, it reframes how we think about AI optimality in a completely new light. The key insight from the research is this: transformers are Bayesian in expectation, not in realization. Now that's a fascinating idea, but what does it actually mean? So here's how they solve it. For any single sequence of examples you feed the model, no, it's not a perfect Bayesian. Those positional encodings create a bias. But, and this is the really genius part, when you average its performance across all possible orderings of those same examples, it becomes statistically perfect. That architectural flaw is actually a feature that makes it incredibly efficient on average. And this whole Bayesian on average approach works incredibly well. I mean, just look at this chart. Experiments on GPT-3 found that it reaches 99% of the theoretical limit for optimal learning with just 20 examples. That's way, way faster than classical statistical methods, which need over 100 examples to get to that same level. Now, this isn't just some abstract, theoretical breakthrough. No way. Solving this mystery gives us a practical, really powerful tool for making AI much, much more efficient. You know, a lot of us have used prompts like, let's think step by step to get better answers from an AI. This is called chain of thought reasoning. It works wonders for complex problems, but generating all those extra reasoning steps is computationally very, very expensive.
How expensive, you ask? Well, using an unoptimized chain of thought prompt can jack up the cost and the time you have to wait for an answer by a factor of 10 to 100. For anyone using these models at scale, that translates to millions of dollars in wasted computation.
But because we now understand how these models learn, we can derive a formula that actually calculates the perfect number of reasoning steps. It balances the cost of generating more thought tokens against the benefit of getting a better answer, optimizing for both. And just look at the difference this makes in practice. It's night and day. Instead of a long, rambling chain of 200 or even 500 reasoning tokens, the formula might tell us the sweet spot is just around 40. And result? We get 90% of the maximum performance benefit, but it's 5 times faster and 80% cheaper. That's a huge win.
But maybe the most profound takeaway from all this is this. The research proves that chain of thought isn't just a clever prompting trick. It is a theoretically necessary process. It's the only way for a transformer to solve problems that are more complex than what its own internal network can hold. It's literally like an external notepad for the AI.
Which leaves us with a final, really fascinating question. If even our most advanced AIs need an external notepad to truly think through complex problems, what does that say about the nature of intelligence itself? It suggests that maybe true reasoning is always a dance between compressed internal knowledge and external, dynamic computation. A powerful thought for both artificial and maybe even our own human intelligence.